Okay, so finally we found something that can be charged quite easily. This one. And you can get these for slides. Let's just bring it. And by measuring how much you can rotate it, how many rounds, you can actually determine what is the force acting on that one. In fact, this is an example where that object is neutral, by the way. Furthermore, it is not a conductor. So here we had already seen cases where even if a conductor is neutral, if you bring a charged object, there will still be a force acting on the charged object and also on the conductor. But this is an example where we have an insulator. So we have to modify our argument. This argument with the conducting object will not hold for this one. Okay, let's go back to our force law, this one, over here. And one point of confusion in this law is how they identify what is this R. This is usually the form that this Coulomb's law is written. This is it written explicitly. Now, how do you determine the direction from this equation? Now, of course, you know that if you have opposite charges, they will attract, same charges, they will repel, but nevertheless, it will be wise to see how we can derive that relation from this expression. How do we use the directions in this vectors? So this is our force law. This is the force acting on Q2 due to Q1. This is the notation. So you see here, if you look at this subtraction is what determines the direction. So R2 is the position of my charge on which the force is acting. R1 is the position of the charge that is acting the force, that is creating the force. So if I am Q2, he is Q1, let's say, I'm a charge, he's a charge. If you want to calculate the force acting on me, you have to subtract his position from my position. That would give you a vector pointing from him towards me. So if you are calculating the force acting on me due to him, so you should just consider the vector pointing from him towards me, multiply our charges. So if the product of our charges is negative, then the force acting on me will be opposite to this vector. So this difference is, remember, this is the vector pointing towards him on me. If the product of our charges is negative, then the force acting on me is in the opposite direction, that is towards him. Or if you want to calculate, let's say, the force acting on him due to him, you first need to consider the vector pointing from him to him. If their charges are opposite, the product Q1 times Q2 will be negative, so the force will be pointing from him to him. Just keep in mind that the direction is this R2 minus R1 is the vector pointing from the force, from the charge that is creating the force towards the charge that is feeling the force. That is this difference. So if you want to calculate, let's say, the force that charge 1 feels due to charge 2, this is 1 over 4 pi epsilon 0. Again, the product of the charges. This difference is the position of the charge that is feeling the force minus the position of the charge that is exerting the force divided by their separation Q. Also, this cube is not a mistake. The force law is a 1 over r squared law, but you say this is a, if you take the magnitude of this force, magnitude of F12, this will be equal to 1 over 4 pi epsilon 0, Q1 times Q2, their magnitude, R1 minus R2 divided by R1 minus R2 cubed. So this will cancel one of this. Times 1 over R1 minus R2 squared. This is our force law. Are there any questions on how to use this one? Sorry, can you repeat? No, not necessarily. It depends on your origin. Where do you choose your origin? R1 and R2 vectors can be different. The difference will not depend on your choice of the origin, but the vector R1 and the vector R2, they will depend on your origin. So for example, if you choose the origin at this point, R1 vector might be over there, R2 vector might be over like this vector. If you choose your origin over here, R1 and R2 are no longer these two vectors, but these ones now. They have changed. So let's say the question is, what happens if R1 and R1 minus R2 is 0? The distance between the two. Well, let's see, how can you bring two charges, 2 point-like charges to R1 is equal to R2? Well, you will hold one, hold the other one, and then you will just bring them together, right? Now, as R1 and R2, they come closer and closer, the force that you need to exert becomes larger and larger. If you want to bring R1 is equal to R2, you need an infinite force. That cannot be. There doesn't exist an infinite force. So there is no way you can bring two charges at the same point. Other questions? So how does two charges influence each other from a distance? That is not something we like. In physics, we don't like two objects that are separated by a distance to be influencing each other. So we invent some new concept that we will call the electric field. Now what we will say is that if you have a charge over here, let's say a charge Q. Now first of all, let's describe what we mean by a field. This field over here is what you call in mathematics. It's not a group theoretical field. In group theory you also have this concept of field. You have flower fields if you go in nature, it's not that field. It's similar to that one, by the way, but what we call a field is that it's just a function. This field is a function. Let's call it a vector field. A function whose values are vectors. So, what do you call a function? Well, you just give it a value, it gives you some other value. That's an ordinary function. A vector field is, in a sense, just like an ordinary function. You give it some arguments, it gives you a function. Those arguments can be the position of a point in space. So here, let's say this is the position R. At the point R, what we call an electric field is a vector that we define over there. This is E of R. At this point, we will see that the electric field, let's call that point R prime. This is R prime, so this is E at R prime. So we just define this function, which at every point in space-time, it defines a vector. So it tells us what is the direction of the vector, what is the magnitude of that vector at every point in space and time. Now, the way we define the electric field is that we put some charge, Q prime, the force acting on the charge Q prime. We know that the force acting on this charge, let's say over here, Q prime, is proportional to the product of these two charges on Q and Q prime. We divide it by Q prime so that it is independent of the charge we have over here. In the ideal case, this is the definition of the electric field, if we could work with point-like objects. Well, in real life, we don't have point-like objects. The charges are always moving around. So in this example, the explanation of why there is still a force, although it is a conductor, will be that the charges, although they are not free to move far away, they can still move from where they are. So if a charge is sitting over here in a conductor, it can be slightly displaced. So that is what creates this force over here. So when we put this so-called test charge over here to determine the electric field, we don't want the test charge to change the position of our object, of the charges. So it should be very small. Now this is how we define the electric field. You put your test charge over here, measure the force acting on it, divide that force by the charge of the test charge, and you should take a very small charge. And this ratio tells you the electric field at that point. If you put this test charge somewhere else, then you determine the electric field at some other point. Well, the force is a vector, so it has a direction and a magnitude. If you divide the charge, it's just a number. If you divide it by the charge, then you get it's still a vector. If you divide a vector by a number, you still get a vector. So that's why the electric field is also a vector. Now, for the time being, this is just a mathematical trick, let's say. What we are going to say is that, okay, so we have this charge over here. I put this plus charge field, let's say, right over here. I bring it here. It will create an electric field everywhere. And when I bring another test charge over here, it feels the electric field at that point, at its position, and that is what is creating the force. So we will be mainly writing this in the form, the force is equal to acting on Q prime is Q prime times E. So the force, we will not be saying that, okay, I have this force over here, which is created by that charge over there. We are just changing our kind of terminology. I will say that the force over here is feeling the electric field over at its position. So it is not really feeling what is somewhere else. It's feeling the electric field right over here. But that is how we define the electric field. Of course, that electric field is created by the charge on the somewhere else. You can imagine it like this. For example, if I come here and push button 1, so they will all push each other. Eventually your friend on the other end will feel a force, but he's not feeling the force directly from me. I'm creating an effect over here, which is creating an effect over there, which is creating an effect over there, and eventually that effect goes all the way to the other side. I'm not exerting a force directly over here. That is what this electric field is also doing. So you put a charge over here. We will see towards the end of the semester that If you put this charge over here, it will create an electric field right in the near vicinity, which will propagate, and eventually it will reach this other point, the position of the other charge, and only when that electric field reaches the other point, this other charge will feel a force. And that is this propagating property of the electric field is what we will call an electromagnetic wave.
How does it propagate? Like over here, their heads or their bodies transfer the force. But in that case, what exactly transfers this?
The electric field.
Right, but what is the electric field?
Electromagnetic field, let's say.
What is it made of?
Nothing. Yeah, you see, we didn't really discuss waves, and we didn't have time to discuss waves in the first semester. But you have a basic understanding of waves, right? So I'm sure you have been to the sea, and there are all these waves. And if you, okay, can you just unplug that? Move to the other side. So you see, this is what we call a wave. There is this disturbance that is propagating. But this wave needs what's called a medium. We cannot talk about this wave without this wire. The wire is not the wave. So what is the medium of this electromagnetic wave? And we will discuss electromagnetic wave in more detail towards the end of the semester. But since you asked, what is this medium? For a long time, people called it ether. People said that, okay, this wave is the propagating in ether. So they tried to measure it, but they couldn't find it. So eventually Einstein just came and he said, okay, we don't need ether. So the medium of electromagnetic waves is the electromagnetic waves themselves.
Wouldn't it be photons? Wouldn't it be photons?
That's not a medium. That's just an alternative way of describing the wave. But this is just kind of a, let's say, foreshadowing of what we will be studying eventually in the semester. So that is why we are introducing this concept of the electric field. For the time being, that's just a mathematical tool. We didn't really change anything. And the electric field here is created directly by the charge over here for the time being. If I change this charge, move this charge, within our description up to this point, if I change the position of this charge, the electric field at this point changed instantaneously within our formalism up to this point. But we will see that the change is not really instantaneous, it takes time. And whenever that change takes time, there's a wave over there. By the way, that's also why we have gravitational waves. You have probably heard of gravitational waves, the measurement. Because Einstein says that gravity also takes time to propagate. If it takes time to propagate, then there has to be a wave, and we have finally detected the waves a couple of weeks ago. It was in 2014, but the data was publicly announced a few weeks ago. Next week on Thursday, by the way, we will have a talk in this classroom in one of the hours on gravitational waves. So I would advise you not to miss that hour. We will have a seminar instead of a lecture on the third hour. Now let's continue with this electric field. Now, some of the things that we will see about this electric field is that, again, this is just a mathematical construct for the time being, but we will eventually see that this electric field has energy, it has momentum, just like a mass. So it's not just a mathematical trick. We will eventually see that this electric field has a physical existence of its own, independent of the charges also. Now let's do some examples. Electric field of a point charge. So let's just imagine that we have this point charge over here, plus Q, and we would like to find the electric field created by this point charge. Now, because of this relation over here, if you have a charge, if you put another charge nearby, and if you are interested in calculating the force, just calculate the electric field multiplied by the charge. So that's why we can just straightforwardly calculate the electric field everywhere and then see what the force will be if we bring some other charge. Now let's put this test charge over here. This is our vector, let's call it R, pointing from the charge that is exerting the force towards the charge that is feeling the force. And Coulomb's law already tells us that F Q prime will be nothing but 1 over 4 pi epsilon 0 Q prime over R squared in the R hat direction. The electric field at the point R will be, its definition is just the force acting on the test charge located at that point divided by the charge of the test charge. This is equal to 1 over 4 pi epsilon 0 Q over R squared in the R hat direction. This is the electric field. Now, if you want to plot the electric field, let's say we have determined that this was the electric field. If you want to show it, so this is our charge, let's say plus Q charge. Now, at this point, the electric field, it's always radial. If the charge is positive, it's always radially outward. If it is negative, it's radially inward. We have a positive charge over here, and the magnitude gets larger as R gets smaller. So at that point, if this is our electric field, at this point it will be larger, at this point it will be larger. And of course, at every point, there is an electric field vector, etc. So just imagine that at every point in space, there is a vector. So if you want to show all of them, it just becomes a mess. Let's look at a dipole. Now, before the dipole, let's look at the electric field of a line of charge. Now, what we mean by a line of charge is that, let's just imagine we have this infinite line, and it carries the charge density. This is the linear charge density. And what we mean by a linear charge density is, let's just imagine we have a very small segment of length dx. This is a very small segment, and it has a charge dq. If it's a very small segment, then the total charge will also be very small. dq is equal to lambda times dx. So what will be the electric field? Let's say at this point, at a distance d. That is what we would like to calculate. Now, this infinite line charge, of course, it's not a point object, so we cannot directly use the Coulomb law. But we know the superposition principle, and superposition principle tells us that I can just divide this infinite line into very small segments, just like this one, calculate the electric field created by each one of these very small segments, and sum them up. So this one will create an electric field in which direction? Let's say this is positive, lambda is positive, just for sketching purposes. So what will be the direction of the electric field created by this dx on this point? This way? This way? This way? Others? The electric field is always along the line. I mean, if you want to calculate the direction of the electric field, what you can imagine is just imagine putting a positive charge over here. What will be the direction of the force that that positive charge will feel? If the charge over here is positive and positive charges, they will repel each other, so the force acting on this one will be in this direction. This is the force. Let's call it dF. Well, we can imagine that there is a symmetrically opposite part segment over here. This segment and this segment are, let me just erase them. This length and this length, they are equal. It's just a symmetric part. It is also dx. And this will also create and contribute to the electric field over here, and it will be pointing again along the line connecting the two. And the electric field, there will be such a contribution. d prime. The x's are identical, so the charges of these two segments are identical. The distances are identical. If the charges are identical, the distances are identical, then the magnitudes of the electric fields they create will be identical. So this vector and this vector, they have the same magnitude. One is pointing vertically up. Now, let's say the vertical components are pointing in opposite direction, but the horizontal components will be contributing in the same direction. So if we just sum these two vectors, this is dE, this is my resultant vector. The sum of the electric fields created by this very small segment and this very small segment, it will be horizontal. And I can do this for any such very small segment. So that is basically telling me that if I just sum all the contributions to the electric field, the net electric field should also be horizontal. So I don't need to bother about the vertical components of the electric field. I can just look at the electric field created, let's say, by this segment, calculate only the horizontal component, and sum only the horizontal components, because I already know that the vertical components, they will just cancel. So the total electric field, let's say this is the x direction, this is the y direction. This is nothing but the sum of the y components of the electric fields created by these very small pieces in the y hat direction. Y hat is the horizontal direction. I don't need to worry about the vertical component. Let's say the magnitude of the electric field created by this one is, well, we have this constant 1 over 4 pi epsilon 0. The charge of this point charge, which is lambda times dx, divided by the distance squared. Well, let's call this as my, okay, this is x. So x squared plus d squared, this is the distance squared. And then I need to take the cosine of this angle. This is theta. So this is also theta. Cosine of theta will give me the horizontal component. But cosine of theta is nothing but d divided by this distance. So it's d over x squared plus d squared square root in the y hat direction. This is the total electric field. Now, of course, eventually we will take dx goes to 0, so we will have infinitely many terms in this sum, and it just becomes our integral. So the electric field is 1 over 4 pi epsilon 0 times lambda times d integral of dx over x squared plus d squared to the 3 halves. And let's say this is x, so we start from here, from this minus infinity, sum all the contributions and go up to plus infinity. So we go from minus infinity to plus infinity. And if we evaluate this integral, you will see that this is equal to lambda over 2 pi d. This is our lambda over, 2 pi epsilon 0 times d in the y hat direction. So this is the electric field of an infinitely long wire. I do suggest you to carry out this integral as an exercise. Any questions on this one? Well, the trick is the trick that we always use. We already know the laws for point objects, but now we want to study extended object, large objects like an infinite wire. We don't know what the force law is for an infinite wire, but what we can do is we can just divide this infinite wire into very small segments. Each one of these very small segments, they will just act like a point source, point object. We know the force law or the electric field law for a point object. This one. Just sum the electric fields created by each one of these very small parts. And sum them up, that will give you the total electric field. That's what we call the superposition principle. Now we will see some easier means of obtaining this electric field. And I didn't memorize the result of this integral, but we will study Gauss' law probably in 2 weeks' time, and we will see that you can obtain this result in just a couple of lines without taking any such integrals. But for the time being, it is also in order to appreciate the Gauss' law, carry out this integral, and how to evaluate this integral, so that you will also refresh your calculus knowledge. We will be using lots of integrals, lots of vector signs this semester. And you were complaining about the vectors last semester. This semester will be all vectors. Now, any questions on this example? These are the basic steps that we will always use. It's like divide and conquer. We have a large object, we divide it into small parts, and once we have these small parts, we know already the laws for the small objects. Just sum them up. Is the electric field and the force, are they in the same direction? Why not? If the charge is negative, you say the force and the electric field are related by this expression. If Q is positive, in that case F and E are in the same direction. If Q is negative, F and E are in opposite directions. If you put a positive charge, it will accelerate in the direction of the electric field. If you put a negative charge, it will accelerate in the direction opposite to the electric field. Well, we don't know if there is a limit on the maximum possible acceleration or not. We don't know. This one. This thing is cosine theta. Well, let's see, what we said was, okay, you see we have these electric fields created by this very small segment. It will be cancelled, the vertical components will be cancelled by the opposite part, the symmetrical segment. So it's enough to take the horizontal part. To obtain the horizontal component of this vector, we just multiply the magnitude of the vector and the cosine of the angle between the vector and the horizontal direction. So if you just look at this here, I want the horizontal component of this vector, so I just multiply it by the cosine of this angle. That angle is the same as the angle over here, but the cosine of that angle is nothing but d divided by this distance.
That expression, because the cosine theta, why is the bracket x squared plus b squared is not squared?
It's not?
It's squared, is it bracket?
Well, you see, this distance squared is x squared plus d squared. The distance is the square root of this one. So you see, this one is the square of this one. I should take the square root of this expression to obtain this distance and take its square to obtain the distance squared. Pythagoras theorem. A squared plus b squared is equal to c squared. This sum already gives me the square of the distance. Other questions? Now I know who to look at to determine whether it's time for a break or not. Okay, see you after 10 minutes.